Okay, so section 1.1 is Intro to Vectors. A vector is a directed line that corresponds to a displacement from a point A to another point B. So examples of what vectors could be would be v, so the vector 1, 3, or the vector u, which is the vector 2, 4. So the vector 1, 3 would mean that I'm going over 1, up 3. So this would be the vector v. So what we call these horizontal vectors are row vectors, and you'll see those more in multivariable calculus. In linear, we mostly deal with column vectors. So, right, u here, it would be a column vector. And then the individual coordinates of a vector are called the components. So the individual coordinates are called the components. So that would be like this 1, 3, or the components of u would be 2, 4. For example, for the vector w, right, w1, w2, wn are the components of w. Now, vector addition is mathematically very simple, or when you're calculating it, is very straightforward. Right, so if I have some vector u and some vector v, then u plus v is just adding the corresponding components of u and v. Right, so u1 plus v1, u2 plus v2, un plus vn. Right, and what's happening here is essentially, if you think about how you would visually represent addition, you're just going, right, tip to tail, so you go all the way up to u, you go over with v, and then if you create a new vector, right, from your final ending point and your starting point, then that is u plus v. Notice also that if I went in the other direction, right, so if I did v first and then u, up to how good I can draw using a mouse, that's also going to take us to u plus v. So you can kind of visually see that, right, v plus u is equal to u plus v. Right, and we call this the parallelogram rule. Okay, scalar multiplication. Given a vector v and a real number c, the scalar multiple cv is given by c, which is equal to c times v1, c times v2, c times vn. Right? So we can kind of put those together. You say, suppose that I have some concrete examples. So if u is 3, 1 and v is 1, 2, like say the vectors that we worked with in class, and I want to find 10 times u plus v. Right? So a scalar multiple times vector addition. Right? Then 10 times u plus v is going to be 10 times 3 plus 1 over 1 plus 2. So 3 plus 1 is 4, right? 1 plus 2 is 3. 10 times 4, 10 times 3 is 40, 30. Right? And notice that this would be exactly the same if I did it going out and distributing, right? 10 times 3 is 30. 10 times 1 is 10. 30 plus 10 is also 40. Okay, so we kind of needed to think about scalar multiplication to talk about vector subtraction. Essentially, u minus v is going to be equal to u plus negative v. The same way that it is with real numbers, but geometrically what's going on is kind of a little bit more to wrap your head around. So if I've got some vector v, right, and some vector u, then if I want to subtract them, I'm going to think about what negative v is. right? So if I've got v, then negative v is just going in the exact opposite direction, right? So if I want to think about u plus negative v, right, well, I've got it over here, right? So instead of negative v, I move it here, because remember, vectors are just about displacement. So this vector negative v is the same as this one. It doesn't matter where we put it. So then this is going to give me u minus v, right? This point here. And note also that another way I can think about this, so this is the way, I'd say the most formal way that's going to lead you to the correct answer. This one is shorter, so if I think about what is u minus v, if I just draw out u minus v at the same, or u and v at the same starting point, then going from v to u is going to give me u minus v, right? So you can kind of see that this vector and that vector, up to my drawing ability, are the same, right? Okay, so let's get into the algebraic properties of vectors. So these are kind of the important geometric points, and using these three properties, right, so subtraction, multiplication, and addition, and really just scalar multiplication and addition, right? So if we've got u, v, and w are vectors in Rn, right, so Rn, right, that just means in n-dimensional real numbers. So, right, a line is R, a plane is R2, like the space we live in is R3, but you know, mathematically in linear algebra we could represent higher dimensions and talk about what's going on even if we can't draw it, right? So, and then C and D are scalars, right? So we got u plus v equals v plus u. We kind of drew that out. Association holds u plus v plus w is equal to u plus v plus w. Right? And we talked in class about the zero vector, but u plus 0 equals u. U plus negative u equals 0, right? And you can kind of think about how that works, right? If I go out and then come back the exact same amount in the exact same direction, it's going to be like I didn't go anywhere at all. Right? C times u plus v equals cu plus cv. We saw that in the example. Now, also vectors distribute across the sum of scalar multiples. So c plus d times u equals cu plus du. And this property can help us out if we're trying to break things up in sometimes to get certain linear combinations. Likewise, c times du is the same thing as cd times u. And 1 times u equals u. Okay, so that is essentially the algebraic properties. And like happens a lot of times with some of these fundamental properties, is they seem obvious, and it's more about the way that we can apply them in situations to get things that we want, ways that might not be obvious at the time. And we'll see that as we go on and have more situations to use it. Okay, a new definition. A vector v is a linear combination of vectors v1, v2, v3, and vk if there are scalars of v1, v2, v3, vk such that v is equal to c1, v1 plus c2, v2 and so on, plus ck, vk. All right, so a couple of things to note about this definition. Here, the vector symbols, so the notation can be a little bit confusing because here I'm not talking about v1 as a component of the vector v. I'm talking about a whole new vector, right? So this vector might be 1, 2, and then this vector is 7, 8, right? So we're saying I've got k vectors, and the reason I'm using k instead of n is I don't necessarily have the number of vectors don't need to be equal to the space that I'm in. So if I'm in R3, right, I might still have k vectors, which could be 2 or it could be 10. So if we have this is equal to a linear combination of other vectors, right, then V is a linear combination. And in this case, C1 through Ck are called the coefficients of the linear combination. Okay, let's look at an example to kind of make that more concrete. So the vector 2, -2, -1 is a linear combination of 1, 0, -1, 2, -3, 1, 100, 100, 100, and 5, -4, 0. And the way that we can see that, so 3 times 1, 0, 1 plus 2 times 2, -3, 1 plus 0 times 100, 100, 100 minus 5, -4, 0 is equal to 2, -2, 1. A couple of things to note here. First, I put this in just to emphasize the fact that 0 is a perfectly valid scalar. As we start talking about linear dependence and independence, sometimes you feel like you have to use every single vector to create a linear combination. And right, 0 times this vector, so 2 is still a linear combination of these. I just don't really need to use that one. And then the other thing, so we can kind of see, right? So 3 times 1 is 3, plus 4 minus 5 gives me 2, right? 0 minus 6 minus -4, so plus 4 is -2, and so on. So that's how we use linear combinations, and essentially like this is a more concrete example of what we were meaning when we talk about that. So in this case, right, like I might say this one is the vector v1 and so on. So like v2, v3, v4. That is it for the first video on 1.1. Still kind of working out the technical kinks, so hopefully these will get a little bit smoother as we go along, but this is going to be what you could expect. I will see you in class.